Hello everyone, this is the video for lecture 20, and today we're going to start chapter 22, Reflection and Refraction of Light. I first want to start by talking about the nature of light. So light can behave in many ways. Basically, depending on how you look at it or how you observe it, light can look like a particle, which we call a photon. Light can look like a wave in the form of electromagnetic waves. We'll talk about light as a ray in the coming slides. And then particles and waves we'll talk about in more detail in the next few lectures. But for example, light can travel through space like a particle. Right? In space, there is essentially nothing. Right? It's a vacuum. So light, if it was a wave, should not be able to travel through space. But of course it does, because this is how light gets to us from the sun. In fact, we even define waves as requiring a medium to travel through, and in space there's no medium. In other cases, we can see that light can spread out like a wave, like if you drop a rock in a pond and the waves spread out from the impact point. We can see that kind of behavior with light as well. And this is not something you would expect if light was simply a particle. Trying to reconcile these two very different behaviors is something we do in higher level physics classes, particularly in quantum mechanics. But for our purposes, we can study both the particle and the wave-like nature of light by applying different models. So I want to reiterate what a model is in physics. Essentially, a model is a relatively simple set of rules that describe some complicated behavior that we observe. Now, models do not have to apply to all situations. You can have simple models that just describe a few things around you, or you could have very complicated models that can try to describe a lot of things in the universe. When we're using models, we just have to be careful to only use the rules when they're appropriate. So as an example, Newton's theory of gravity that we learned about in the first semester, this works very well when we describe motion that's close to the Earth. It also describes the orbits of the planets very well. However, it does not describe speeds that approach the speed of light. So if you start traveling very close to the speed of light, Newton's theory of gravity does not work. If you're dealing with something that has an extreme density, like for example a black hole, or even a large sun, Newton's theory of gravity also doesn't work. Newton's theory of gravity has trouble explaining the rotations of galaxies, and I could go on. But the point is, Newton's theory of gravity works well when it works. When it doesn't work, we have to use some other theory. So you might be wondering, which is it? Right? Like maybe light sometimes behaves like a wave, but it's really a particle, right? Or vice versa. Well, here's the thing. Light is light. Right? It just does what light wants to do. Nature, the universe, does not behave according to our laws. We create these laws to describe what we see around us. But nature does whatever it wants. And with light, we associate properties that we're familiar with. We study particles a lot. We study waves a lot. Historically, we studied particles and waves separately. Then we discovered that light actually has some of both of these properties. So light is something different. What I might describe it as in a higher level context is a quanta of energy. Quanta is the plural of the word quantum, and basically this just means a little packet of energy. We'll start with what we call the ray model of light. So we're going to think of light as a ray, just a beam of light that comes out of a light source, like the sun or a light bulb. Some of the basic principles of this model are that light travels in a straight line. As long as light stays in a uniform medium, so if light stays in air or if light stays in water, then we can say that light travels in a straight line. That's what's shown on the right. You have straight lines coming out of the sun. They're coming out of the sun in all directions. So light is emitted by some objects, often in many directions. The sun is emitting the light in all sorts of directions. When you're relatively close to the sun or a light bulb, those rays might be coming out in all directions. But if you're very, very far from the sun, so if you're looking at the light rays in this region over here, those rays start to look more and more parallel to each other. We will assume that light can pass through some objects like glass and air. We will assume that it does not pass through some objects and that it scatters off of them. So this blue cylinder, you have light coming from the sun. It passes through the air. It reflects off of the blue cylinder, and the cylinder may reflect it in all sorts of directions, depending on the surface of the cylinder. Generally speaking, we find that some light is scattered, reflected off, and some of it is transmitted through. When you look at a pane of glass, you'll see, most of the light comes through, of course, but you can also see a little reflection in the glass. So some of it is scattered off and some is transmitted through the glass. And then finally, we will assume that we only see an object when light comes from that object and enters our eyes. So in order for these eyes on the right side to see the blue cylinder, light has to come from the sun. It has to reflect off of the cylinder and then enter our eyes. And that's how we see the cylinder. So then question. You start with a point source, like this one near the center. This point source is emitting light in all directions. Some of that light passes through these two holes in the dark screen. The light will show up on the viewing screen in the back, and the question is, what pattern of light do you see on the viewing screen? On the left, I have a side view of this situation pictured. So here you have a point source that's emitting light in all directions. Some of that light is going to pass through the holes in the dark screen, and it's going to appear on the viewing screen in the back. What pattern do you see? Now, I'm not going to give you the answer now, actually. What we're going to try to do is discuss these questions during our team meetings on Tuesday and Thursday evenings. But I will give you a hint. Think about the light source emitting light in all directions, and that light traveling in straight lines. Here you have a very similar question. Instead of two holes on the viewing screen, you have one hole in the center. And instead of one point source, you have 2 point sources of light. So then what pattern of light will you see on the viewing screen in the back? Again, think about it, and I will give you the answer during one of our meetings. And finally, another similar question. This time, instead of a point source of light, you have an L-shaped light bulb. So light will come from this L-shaped light bulb. It's going to pass through the hole in the dark screen. It will show up on the viewing screen. And which of the patterns below will you see on the screen? On this slide, we talk about reflection. Let's first look at the picture in the bottom right corner. You start with an incident ray of light coming in and approaching this reflective surface. the light hits the surface and reflects off. After it reflects, we call it a reflected ray. So you have the incident ray and the reflected ray. You have this line in the middle called the normal line. The normal line is a line, or any line, that is perpendicular to the surface of reflection. So if I draw a vertical line on the left, this line could also be considered a normal line. If I draw a vertical line on the right, this could also be considered a normal line. So a normal line is any line that is perpendicular to the surface. And then you have two angles. You have this angle theta 1. This is the angle that the incident ray of light makes with the normal. You also have a theta 1 prime. This is the angle that the reflected ray makes with the normal. So the incident ray does not have a prime. The reflected ray does have a prime. And both of them are measured to the normal. Essentially, what you have to do to measure these angles is look at where the light ray strikes the surface, where it reflects off the surface, draw the normal line at that point, and then measure the angle between the incident ray and the normal, and then also measure the angle between the reflected ray and the normal. Okay, so at the top we have a ray of light strikes at angle theta 1, reflects at angle theta 1 prime, and that first bullet point tells us that theta 1 prime is always equal to theta 1. So the light reflects off at the same angle that it's incident upon the surface. The second bullet point tells us that the incident and the reflected rays are both in the same plane. So if you view this slide as an XY plane, then the incident ray lies in the XY plane. The reflected ray then has to also be in the XY plane. Essentially what this means is that the rays do not reflect off in random directions. You don't have an incident ray that's moving alongside this slide, and then when it hits the surface, it doesn't just fly out of the screen. And then an important note here, you have to remember to measure all of the angles relative to the normal. This is a very easy thing to forget, and I find that it's a very common mistake among students. Technically, you might say there's more than one kind of reflection. So if you have a mirror or a polished metal tabletop, when light reflects off of that smooth surface, we would call it specular reflection. Essentially, the outgoing light rays, the reflected light rays, they look ordered. In the pictures on the left, you can see that all of the light rays come in parallel to each other, and after they reflect, the outgoing rays are also parallel to each other. Right, this surface is very smooth, so there's no funny business going on. This is something you can see in experiment in the bottom left picture. You have an incoming light ray in the form of a laser. The light ray reflects off of some smooth surface, and the reflected ray reflects off in a very ordered fashion. So what we should technically do is draw a normal at the point where the light ray intersects the surface. So we draw a perpendicular line at the point of intersection, and then we want to measure the angle from the normal to the incident ray, and we want to measure the angle from the normal to the reflected ray. And just by looking at these pictures, you can see that theta 1 is roughly equal to theta 1 prime. Right? If you were actually doing this experiment, you would have to be more careful about that measurement, of course. Not all surfaces are so smooth. In the bottom right picture, you have that same laser beam coming in, but when it hits the surface, it reflects off in all directions. You can see this big blur of light in the center reflecting off in all directions. And this is what you would see if you took a laser and pointed it at your wall or at your floor. Those surfaces are just not as smooth as a mirror or a polished tabletop. So when light reflects off of a rough surface like this, we call it diffuse reflection. So the outgoing rays, if you look at them as a whole, they're scattered in all sorts of different directions. In the diagram in the top right, you have light coming in parallel to each other. But after it reflects off the surface, those light rays scatter in all sorts of different directions. I do want to point out that if you look at each individual ray, it still follows this law of reflection, that theta 1 is equal to theta 1 prime. If you look at the topmost one, for instance, it comes in, it reflects off the surface. If you draw a normal line and then measure the two angles, you'll find those two angles are equal. And let's look at the second from the top one. Here you have a light ray coming in. It reflects off, and it doesn't look like it reflects off at the same angle as the top one that we were looking at. However, if you draw a normal line at the surface here, you'll see that the surface is actually slanted a little bit, so the normal line is not perfectly vertical. If you were then to, well, first of all, if you would have drawn the normal line correctly, and then if you were to have measured the two angles, you would find that those two angles are equal. For our purposes, we're going to essentially just assume that all reflection is specular reflection, unless told otherwise. And that's pretty much all I want to cover today, at least as far as the course goes. But since the lecture is a little short, I thought I'd take a brief aside and talk about black holes, since black holes and light, they're kind of related in a way. So black holes are objects that have gravity which is strong enough so that nothing can escape from it, not even light, and that's where light comes in. Remember, we assumed that you can only see an object if light reflects off of that object or is produced by that object and then enters our eyes. If light bounces off a black hole and it cannot escape, that light can never reach our eyes, so we can't actually see black holes. Black holes come in many sizes. You can have very, very tiny ones that can fizzle out in just a brief instant, a few nanoseconds. And you can also have massive ones that essentially last forever, and they're even big enough to hold galaxies together. The picture in the top is an artistic rendition of the Milky Way galaxy, our galaxy. And at the very center of our galaxy is a black hole. The gravity from that black hole is holding all of the stars of the galaxy together. You might wonder why the center is so bright if the black hole is sucking all the light in. Well, there's also a lot of stars near the center of the galaxy that are still emitting a lot of light. Now, you don't just get sucked into a black hole as soon as you get relatively close on a galactic scale. In fact, the gravity of a black hole behaves exactly the same as the gravity of any other massive object in the universe. Just like with Earth and just like with the Sun, the gravity of the black hole gets weaker the further you are from that object. In fact, if you were to, say, replace the sun with a black hole that has exactly the same mass, gravitationally speaking, we would not notice a difference at all. It would get very dark relatively quickly, but Earth would still revolve around that black hole just like we revolve around the sun. So if you're talking about large distances, like say from the sun to the Earth, gravity feels like normal. When you get close to a black hole, gravity gets stronger. And this is true for the sun as well. But the point is, with a black hole, you can get close enough that at some point you can no longer escape that gravitational pull. That point of no escape, this is called the event horizon for the black hole. Now, black holes are notoriously difficult to photograph since they don't emit light. But in April of last year, physicists captured what we call the first image of a black hole. And this is what's shown in the bottom right here. This black hole is 54 million light years away. So the light that's coming to us in this picture came from the black hole 54 million years ago. So light can't come from a black hole, which means the light in this picture doesn't actually come from the black hole. What we actually detect here is light given off by the space dust surrounding that black hole. And that light comes to us in the form of radio waves. So the space dust that's swirling around just outside of the black hole, it heats up because of the gravitational force of the black hole. Then that heat causes the space dust to emit light in the form of thermal radiation. Then by the time that light gets to us, it's a radio wave. So we detect those radio waves and we use that to create this picture that's shown in the bottom right. So if light can be sucked into a black hole, if I draw a black hole up here, and light can actually be sucked into that black hole, then light rays which pass close by, but not inside of the event horizon, they can be bent from their normal straight path. So if I have another light ray that passes near the top of it, as long as that light ray doesn't cross the event horizon, that light ray will be bent from the straight path. We call this gravitational lensing, and we actually have photographic evidence of it, and this is what we see in the picture here. If you look closely at all the galaxies in this picture, you can see that many of them seem to sort of be bending around some central location. You have one here that's very much stretched out. And if I sort of trace a bunch of these, you can see that it looks like they're all circling some central location. I don't know, maybe somewhere around here. What's happening here is gravitational lensing. These stretched out galaxies are somewhere very far away from us. And somewhere between us and those galaxies is a black hole. So you have, we're located over here. You have some galaxies located very far away. And then somewhere between us, there's a black hole. Now light from these galaxies tries to pass by this black hole. As it passes by, it gets bent. And it gets bent so that it does reach us on Earth. So then what we see is this distorted image of the galaxy. So even though you can't see the black hole in this picture, you can see the effects that it has on basically all the light that you can observe. And interestingly enough, the galaxy in the picture that I drew at the top, this galaxy is located directly behind the black hole as far as we're concerned. because of the way that light bends around the black hole, we can actually see objects that are behind it. Right, if light only ever traveled in perfectly straight lines, it would be impossible for the light from this galaxy to reach us, because all of the light from that galaxy would be sucked into the black hole. But since light bends around the black holes, we can actually see what's behind them. Black holes, of course, are a very popular topic in science fiction and pop science, but they're also very popular among physicists. And for this reason, black holes are a very active field of research. In 2016, some scientists detected gravitational waves from the collision of two black holes. They then converted those gravitational waves into sound waves, and this is the noise that they got. To me, that sound is mildly interesting, but one of the coolest things I've ever seen in physics are these GIFs at the bottom. So what they did was they pointed telescopes at the center of the Milky Way galaxy. Then every month or so, over the course of 20 years, they took a picture. At the end, they compiled the pictures into these videos that you see. Now, stars we generally think of as not moving very much. Right? We usually picture the solar system as the sun in the center, and then we rotate around the sun. And we don't really think about the sun as moving a whole lot because it's so large and it's the center of our solar system. But in these videos, you can see stars that are moving quite a bit. These two videos are the same, by the way, just the one on the right they zoom in on. So you can see all of these stars, they're all rotating, and they're all sort of rotating around some center point right around here. One of the stars in particular you can see rotate quite a lot. A few of them, I guess, once they zoom in. And in the video on the right, once they zoom in, they actually trace the orbits of the stars. And if you remember back from last semester, the orbits should be elliptical, and you can see that that one star has a very elliptical orbit. And at one of the focus points for that ellipse is a black hole. So somewhere around here, there's a black hole. So all of the stars in the video are orbiting this black hole at the center of our galaxy. The numbers in the top left of this video are the years, of course. And on the right, they give you the scale, measured in light days. So actually, these stars are moving quite a bit. For reference, the sun, our sun, is located 7 or 8 light minutes away from us. So what you see here, right, this distance here, that's how far light travels in 10 days. And these stars, these huge, massive stars, are traveling on the order of this distance over the course of 20 years. You can read more about this at the space.com link that I put on this slide. And then one more thing, because I do hear this sometimes. Sometimes people think that black holes just zip around the universe and they just eat everything they come across. This isn't exactly true. Black holes behave just like other massive bodies in the universe. All right, I mentioned this, if you replaced the sun with a black hole, everything would go on the same. It would just be a lot darker. So black holes, they don't just go around eating everything in the universe. And then the final slide today. You might wonder what would happen if you went inside of a black hole. So the short answer is that you would not survive, and nothing would. Even other black holes wouldn't survive in a bigger black hole. The longer answer is that as you approach a black hole, you would see no light coming from the black hole because the black hole sucks in the light. Around the outside of the black hole, around the event horizon, you will see stars that become distorted, and they'll get more and more distorted as you get closer and closer. This is because gravity is bending the light rays. Then the interesting bit is that you would be spaghettified because of the difference in gravity felt between your feet and your head. And this is shown in the bottom right. As you get very close to that black hole, the gravity gets stronger and stronger and stronger. And when you get close enough, you get to the point of no escape, that event horizon. Right? So the astronaut's feet are very close to the center. His head is a little bit further from the center, but the difference in gravity between his feet and his head is so strong that his feet start to get pulled into the black hole before his head gets pulled into it. This causes the astronaut to stretch out, or what we say spaghettified, or spaghettification. So this all happens as you're approaching the black hole. Once you enter the black hole, basically all the atoms in your body are crushed into the singularity at the center of the black hole. Okay, so now all of that said, I should point out that the physics of inside a black hole, or even near the event horizon of a black hole, this is largely unknown, and people study it a lot, even to this day. So everything I said, it's based on our current understanding of the universe, but it is mostly just speculation. And then if you look to sources like science fiction or popular science, they like to speculate even more. A lot of times sci-fi equates black holes to wormholes, wormholes being sort of like portals from one area of the universe to another. This seems very unlikely to be the case, but it's possible, and some physicists even try to devise ways in which this could actually occur in our universe. That's all for today. I hope you enjoyed the little side topic on black holes. Next time we will continue chapter 22, and we will start talking about refraction. Have a good one.